All right, so this is the second meter for the practice. Actually, this was from the last spring semester. So the format is very similar as the first meter. So first you have the true or false. So here again, the correct answer are worth 2 points. Incorrect answer will result in -1 point. So if you are uncertain, please leave it blank to avoid these negative points. So this is to discourage the random guess. All right, so pay attention to this policy. And then let's get started. So the first statement here, when the MOSFET is in the triad region, it could be approximated as voltage-controlled current source. So is this true or false? I'll give you like 10 seconds to think over. Yeah, you can type in your answers through the chat. So MOSFET, if you think of the MOSFET, in the triad region, that means the VGS minus VT is larger than VDS. So if you recall the lecture 9, or maybe lecture 10, so when we talk about the MOSFET, 3 regions, cutoff, triad, and the saturation, we see that the triad region, if you think about the IDVD, so this is the triad region, right? So this triad region, the ID is proportional to VD to the first order. If you only take the straight line here, then it's like a resistor, right? So this is like a resistor. So this is false, because in the triad region, this is more like a resistor. Only when this is in the saturation region, then we have a constant current to the first order. Then it's like a voltage-controlled current source. What voltage controlled? That should be the VG controlled. Because as you change the VG, you are going to have different curves. So the gate voltage will control this current level in the saturation. So in the saturation region, it could be approximate as the voltage-controlled current source. So this is a false. Okay. And second one, for a PMOS, the source and the drain are heavily P-type doping. Is this true or false? 10 seconds for you. So this is true. So for the NMOS, normally we talk about NMOS. NMOS is N plus for source and drain, then the P-type substrate. So this is NMOS. And PMOS is just the opposite. So you have P plus source and drain, and then N-type substrate. So this is true. The third one, if we consider the channel length modulation effect, the MOSFET will increase, MOSFET current will increase with the drain voltage, even in the saturation. So 10 seconds for you. channel length modulation. So this one is talking about the second order effect. That is, the channel, the pinch-off point is going to move to the left when the transistor is in the saturation. That will make the current larger because the effective channel length will be reduced. So that will be reflected to this IDVD. So that means in the saturation, the current is going to increase further. So this is true. Okay, so number 4. Definition of the source and drain in the MOSFET is arbitrary. For a PMOS, lower voltage potential is the source. 10 seconds for you. PMOS. So PMOS, this is the gate. This is source, this is a drain. For example, this is your VDD. So VGS is here. So here you can see that this source is attached to the power supply. So this is higher potential side. Then this is the source. So it says no, this lower potential is the source, but actually should be higher potential for the PMOS. Okay, number 5. When 5 CMOS inverters connect in a loop, it becomes an oscillator. True or false? For NMOS, if you recall the symbol for NMOS, this is ground. So the arrow here represents N and P. Number 5. 5 CMOS inverter in a loop. So this is true. We talk about the inverter in a loop. So if you have 5, then basically odd number like 3, 5, 7 will make this oscillate. This is in the lecture 13 when we talk about the CMOS delay. We have odd number of inverter in a loop. It becomes oscillator. This is true. All right. So number 6, when the threshold voltage of MOSFET increase, both on-state current and off-state current, I on and I off, decrease. True or false? So if you think about the log scale of the ID versus the VGS, this is to show the subthreshold loop. So we have something like this, and this is like the threshold voltage. And here we have the I on, and here we have the I off. So this is from lecture 10. Now the threshold voltage increase. That means this is going to increase. So this curve is shift like this. So both off current and on current should decrease. So this is true. Also from the on current equation, the saturation current is mu COX W over L VGS minus VT squared. If VT increase, then the drain current decrease. So this is for the on current. So you can also say that the on current decrease when you increase the threshold. Okay. So this one is true. Number 7, the delay in a CMOS inverter decreases if the transistor on current increase. So how about this one? The delay. So any delay, if you recall, like delta T is due to the charge delta Q, which is C times voltage, for example VDD, to the first order. And then 2 times of the I average. This is a definition of the TP. And then to the first order, we see is on current. If on current increase, then the delay will decrease. So basically your transistor is going to charge and discharge the capacitor load faster because you have larger on current. So this is increase, so then this is false. Should be decrease. Okay, so number 8, static power in a CMOS inverter decrease if power supply voltage decrease. Static power. So first of all, you need to understand there are 2 kinds of power dissipation. One is this static, the other one is a dynamic or active. Static means you are doing nothing. Okay, the input keeps the same. You don't have the 1 to 0 or 0 to 1 transition in the input. So the input is static. It's like in your standby mode or sleep mode of your smartphone. So we talk about the static power is due to this leakage from the off current through the transistor. And if you recall, the P static is just the I off times VDD. Because this current comes from the power supply VDD. So if you reduce VDD, then the static power reduces. So this is true. Yes, VDD is a power supply. And then dynamic energy, number 9, dynamic energy in a CMOS inverter in 1 clock cycle is half. CL is the capacitance, the load, and then VDD squared. So true or false? Dynamic energy in 1 clock cycle. So this is false, because in 1 clock cycle should be C VDD squared. 1 clock has 2 half cycle, one rising edge and one falling edge. So each edge consumes half. For example, the rising edge of the input, then the output is the falling edge. Then the falling edge, NMOS is working, so NMOS will consume half of those energy. And then the next half cycle, then the PMOS will consume the other half. So in total is CVDD square. Now last one, to make the voltage transfer curve of a CMOS inverter symmetric, the NMOS needs to be wider than the PMOS. So this is on the match condition for the CMOS inverter. Voltage transfer curve symmetric means match condition. So the match condition mu n W over L n should be the same as mu p W over L p. And we know mu n is larger than mu p because electrons move faster than the holes. Then the W over Ln should be smaller than W over Lp. So PMOS should be wider. Then this is false. Okay, so any questions on the true or false here? So those are some conceptual questions, and if you review the lectures and go through the concepts, then should be able to address those true or false questions. All right, so then let's move on. Question 2. So consider the band diagram of the MOSFET along the channel direction. And just choose which case represents the band diagram when the gate voltage is larger than 0 or positive gate voltage. So here we are going to show the MOSFET MOSFET band diagram. When the gate voltage equals to 0, that's the solid line here, this one. Then we show case 1 and case 2. So the question is simple, just choose which case represents when the gate voltage larger than 0. Just choose 1 or 2. Any idea? Case 1 or 2. If the solid line is gate voltage equals to 0, then which one is gate voltage larger than 0? Or in other words, when this is NMOS, okay, this is NMOS transistor. So in other words, when you apply positive gate voltage to the NMOS gate, the band is going to be pushed down or pushed up. Case 2, because we talked about before, right? So when you apply positive voltage on the energy band, it's going to push down the band edge. This is like EC, the conduction band edge. And then for this PMOS, when you push down the band edge, the barrier between the source and the channel is going to reduce. That's why you have more electrons will move over the barrier if you have the drain voltage. So that's how the transistor electron can flow, because the barrier is reduced when you apply positive gate voltage to the NMOS. So this is case 2. Okay. And then let's look at the next. So current versus voltage. So basically IV. And we assume the square law model. That means the first order equations for the IDVG or IDVD. And the source is ground. So indicate those 3 regions in this figure. Okay. So this figure is ID versus VG. And the question is ask you to label the 3 segments in this curve for the 3 regions. You know, we have the cutoff and the saturation and the triad. So the question is ask you to label those 3 segments in this IDVG curve. So how do we do that? So first of all, here, this one, you see this current below this is almost 0. So you know this is the threshold voltage, Vt. Therefore, this part will be the cutoff. And then we see a second turning point is here. So after that, this is like a linear. So you think about the transistor. So here, this IDVG curve basically is with some fixed Vd at a certain Vd. But here we are going to increase or sweep the Vg from 0 to 5 volts. So the Vd is fixed. And then we increase the VGS. So when the Vg, of course, is smaller than the threshold, then, for example, smaller than 1 volt, then it's cut off. Then as we increase the Vg above the threshold, but still VGS is small. So Vg minus Vt is very small. Small, let's say smaller than the Vd. If VGS minus Vt smaller than Vd, is Vt, because here is just 0, and then when you increase a little bit, then still the Vg minus Vt is a small number. For example, here, maybe point something. So compared to the Vd in this region, this one is probably smaller. So in other words, this is a saturation. Still here, you see a turning point. Above that, because the Vg is very large now, next 4 volts or 5 volts, so the Vg minus Vt is also larger than the Vd. Then this is like a triad or the linear region in this part. So basically, we have 2 turning points here and here. Okay. So the second question here, what value of the Vd corresponding to this IDVG curve? So here the question is, what is this VD? We should use this turning point. So this turning point give you the VD, give you the VT, the threshold. So the second turning point will give you some information. That is, because here is the boundary between the saturation and the triad. So this boundary, if you recall, that is this one, right? So we are comparing Vg minus Vt versus the Vd. So that is the boundary. So this Vg here is like 3 volts. Vt is 1 volt. So this boundary is 2 volts. So here the Vd is 2 volts. All right, any question? So here in this curve, we can determine the threshold voltage and also the drain voltage. Okay, so this 2.3, then 2.4. 2.4 is regarding this IDVD, and this is similar as your homework. So it says, okay, so this IDVD is when the gate voltage Vg equals to 4 volts. So here's ID versus Vd is measured when the Vg is 4 volts. Then the question is, what is the threshold voltage of this one? If you use this IDVD, you can also determine what is the threshold voltage. So how to do that? So in this curve, you see one turning point here. So then we should use this turning point to do something. So this is ID versus Vd. This is different from the previous ID versus Vg. So in IDVD, you know this part is the triad, and this part is the saturation. This is the boundary. So this boundary again will be Vg minus Vt equals to Vd. This is the boundary condition. So Vg here is 4 volts minus Vt equals to Vd. Vd, what is Vd? Vd is here, this one is what? 3. So Vt will be 1. Volts. All right. Then the last question here, calculate the saturation current at Vg equals to 3 volts. So in this plot, we show the Vg equals to 4 volts. But now we want to determine the current, the saturation current when the Vg becomes 3 volts. So basically, you may draw another curve. Or maybe let's draw it. For example, if this one is the Vg equals to 3 volts, the question is, what is the ID when the Vg equals to 3 volts? This is asking for the saturation current. So saturation current so this is the equation. So first of all, for this one, you'd better write down this kind of equation so we can apply partial credit. So you'll see that we're going to calculate the saturation current. So write down this equation first. And then from this Vg equals to 4 volts, you have the 1.43 milliamp. And mu n CLX W over L. So Vg minus Vt is 4 minus Vt, we just got it, 1. So you have this one. Now we want to know what is the current. When the Vg becomes 3 volts, so it still is like 3 minus 1. What you can do is to calculate this coefficient in front of the voltage terms. So you have this coefficient. From here you can calculate this one and then plug into the second one. You will get the current. Or if you want to make it simple, you just divide those two equations. So it's like 143 divided by ID. So then once you do the division here, then it's cancelled out. So what is left is just this. So it's like 4 minus 1 is 3. 3 squared is 9. And this is 2. 2 squared is 4. So you see the ratio. So the ID will be just move it crossover. So it will be 1.43 times 94, and you get the number. All right. Any question about this one? So I think we have solutions attached. So I don't have the calculator here. So if you do it, then it's 0.636 million. Okay, so this is similar as one of your homework. And then let's move on to the Q3, the inverter characteristics. So consider the CMOS inverter, like this one. And then the first is to draw the VTC, voltage transfer curve, and the current versus the input voltage. Draw the general shapes. Assume the NMOS and PMOS are matched. So here we have this template. We want to draw the VTC. So if you recall the lecture, we talked about the VTC, voltage transfer curve. So when you increase the input voltage from 0 to VDD, the output will decrease from VDD to ground, but then this will follow this shape. So this is this VTC, voltage transfer curve. And this is matched. So the VM points will be half VDD. And second, draw the ID versus the input voltage. So when you increase the input voltage from 0 to VDD, this current from both NMOS and PMOS should be the same. this current is continuous, and this current is going to change as a function of the input voltage. And this kind of plot is in one of the lecture slides. But as you can analyze here, when the input voltage is low, then the NMOS is off, then the current will be 0. Until the input voltage is high enough, larger than the threshold voltage of the NMOS, then current will increase. As the input voltage further increase, current will further increase. So it will increase. When the input is to the Vm point, the current should reach the maximum. And after that, although NMOS is fully turned on, then the PMOS will become the limiting factor, because as you further increase, the VGS of the PMOS is going to reduce. So the current from the PMOS is going to reduce. Even though NMOS can take a lot of current, but the current actually is coming from the PMOS. If the PMOS current is limited by the reduced VGS here, this is the VGS for the PMOS, then the current will reduce. And eventually the current will go to 0, because here if the input voltage is high enough, then the PMOS will be off, then there's no current. So you have this kind of shape. This is to the peak. So saturation is W over 2L, that's correct. So saturation current, you have the half in front of the current equation. All right, so then that's the one. So the Vm is defined as when the input equals to the output. So here, given a fixed NMOS width, if the PMOS width increase, redraw the VTC with dashed line on the same plot here. So basically the question is saying that now the PMOS width W increase. How would the VTC shift? PMOS increase W. And I think we have some general guideline discussed in the lecture about the strength of the NMOS and PMOS. So which one is stronger? So the matched condition says both NMOS and PMOS have the same strength, or they are equal. PMOS become wider, then PMOS becomes stronger in terms of the current drivability, or in terms of the conductance. So PMOS becomes stronger. And we have a rule for the NMOS and PMOS. So what is the role of the NMOS in the inverter? NMOS is to pull down the outputs. PMOS is to pull up. Okay. So PMOS is to pull up this output node. So now the PMOS becomes stronger. Then it's easier to pull up, or in other words, it's more difficult to pull down. So this VTC curve is going to pull down the output. Now it's more difficult to pull down. That means this VTC will shift to the right. So the logic is PMOS wider, stronger, relatively NMOS weaker. So then it's less likely to pull down. Then you have this VTC shift to the right. Okay. Then will the Vm voltage increase or with this? So this is a follow-up question. So it's obvious from this VTC curve, right? So the Vm voltage is defined as, here if you draw a straight line, it's like y equals to x. That is when the input equals to output. So here the Vm, you see now is increasing. Oops, where is it? So now the Vm is increasing if a PMOS increase. So basically based on the shift of the VTC, we can decide the Vm increase or decrease. And actually there is an analytical equation to calculate the Vm. If you refer to the equation sheet, then there's an analytical equations to calculate Vm. And I believe you have done that in your homework as well. All right. So that's Q3. And finally, we have the Q4. So this is the CMOS inverter delay and power. So here we have the parameters for the CMOS inverter, like the power supply VDD and the threshold, and mu n COX, mu p COX, and the capacitor load is 10 femtofarad. So this is the circuit. And we have NMOS W over Ln equals to 1. And the clock on this inverter from rising edge to rising edge is like 1 gigahertz. Okay. Then here we are considering the output high to low transition. So input is low to high and output is high to low. So input has assumed a perfect rectangle input waveform, but the output will take some delay for the output waveform to decay. So this is what we assume for the TPHL, high to low transition. The TPHL is defined as when the output voltage decreases to half VDD, 50%. And we have the point A and point B. That is the starting point and the ending point, or initial state and final state in this decay process. Okay, so then let's look at the question. What is the transistor QN NMOS operation region at point A and point B? So it asks, what is the operation region? Operation region, you can only choose from like the cutoff, saturation, and the linear, or the triad. So you have those options. And at point A, which region? Point A is here when the input is already VDD. So point A is input is VDD. And then point A, here output has not decayed yet. So the output is VDD. So that is point A. So at point A, your VG is VDD. Your VD is also VDD. Then you have VG minus VT smaller than VD. Then this is saturation, right? How about point B here? So the input always kept at VDD, right? So input is always VDD. That means the gate voltage is VDD. But now the output changed to half VDD. Output is the VDS for the NMOS. So the VD becomes half VDD. Then VG minus VT compared to VD. Now you have to plug in the numbers. because the first one, this one is for sure, because VDD minus something, of course, is smaller than VDD. But this one is VDD minus VT compared to the VD. So basically, it's VDD minus VT compared to half VDD. Then depending on the numbers. So if you look at the question here, VDD is 1 volt, VT is 0.3. Then we have to plug in those numbers. So this is 1 volt minus 0.3, and this is 0.5. So this is 0.7, larger than 0.5. So now this is different, right? So this is larger. So this is triad. Any questions? And then it asks to calculate the TPHL using the average current method. And to simplify your calculations, the current at the point A and point B are already given as below. So that means here the current initial and the final are given. Then to calculate the TPHL. Average current, right, TPHL is capacitance of the node times VDD divided by 2, half VDD, because you change by half VDD, and then I average. So you should write down this equation first, get the partial credit. And then the average current, is the average of those two. It's average of those two. And basically you plug in the numbers, like the capacitance is 1 femto, and VDD is 1 volt, 2, and times those two numbers. So, and you can do the calculation. I will skip that. But be careful about the unit. The femto, is minus 15, and the micro is 10 to minus 6. So I will skip the calculation, and I think the number, the final solution is given here. I don't have the calculator here, so you see here it's this 70.9 picoseconds, pico, 10 to minus 12. Okay, let's go back. And then the 4.3, find the W over LP for the PMOS to make the low to high delay. TPLH is the same as the high to low. I think that's a typo here. So high to low delay, the same. So here, this one, the NMOS W over L is given from the question, but PMOS is given. So it asks, what is the W over LP to make the high to low transition delay the same as the low to high? So if we interpret this correctly, then this is asking for the match condition. Because if it's matched, then the NMOS and PMOS are equivalent then high to low and low to high transition should have the same delay. So basically it asks for the match condition. Then it's straightforward. The match condition, you see the mu n and mu p here is given, the ratio. So the match condition, so basically here is asked for the match condition. Match condition, you know, is this one, the same as this PMOS. So this one I think is 300 from the question. W over Ln is 1 from the question. And this from the question is 150. And you can get the W over Lp very easily. So it's just a 2. So PMOS needs to be wider because mobility in this case, the ratio mu n over mu p is like 2. And then 4.4, the last one. What is the dynamic switching power for the inverter if it switch every clock cycle? So it's asked for the dynamic power. So dynamic power, you first use the correct equation. It's alpha F C VDD square. So this is due to the charge and discharging. Your input is changing from 1 to 0 and 0 to 1. And it says every clock cycle. That means this alpha is 1. That is the activity for the switching. So every clock cycle you are switching, then it's like 100%. And then clock F is the clock frequency. So it's 1 gigahertz given in the question. And C, I think it's a 10 femtofar, right? Let me see. So here, yeah, 10 femto. The clock is 1 gigahertz. Yes, 1 gigahertz and 10 femto. So 1 gigahertz and 10 femto. And VDD is 1 volt square. So then this is straightforward. So this is giga is 10 to power 9. Femto is 10 to minus 15. So then you have 10 times 10 to minus 6 watts. Or in other words, it's 10 microwatts. All right. So yeah, I think that's all for this practice exam. Any questions here? And you can review the solutions by yourself afterwards. And of course, review your homework and the examples in the lectures. So you may see some similar questions in your real second midterm. I would say that your real second midterm next week will have one more question than this one. This practice exam was from last spring, but at that time we have the only like the class scheduled class hours, like 1 hour and 15 minutes for this practice exam. But since this semester you have 24 hours, so I add one more question for you. So you will see one more question for your real second midterm. Yes, the second midterm basically covers the materials from your homework 3 and 4. That's correct. Any other questions? If not, then we can and stop here for today. And we will have a virtual review next Tuesday on the key concepts and the equations in the equation sheet. So you have another opportunities to review. All right, thank you. Bye-bye.